Hello, I'm Kelby, and today I'll be talking about some new classes of vulnerabilities that I discovered earlier this year that affect single sign-on systems. These vulnerabilities were discovered recently and pretty generally applicable to multiple systems. And in some cases, these vulnerabilities enable authentication bypasses and allow attackers to pivot from one user account to another. So a quick thing about me before I dive into my research. So my professional and research interests are in cryptography, mathematics, and security engineering. So if you like those things, feel free to check out my blog or Twitter. At Duo, most of my time is spent as a security advisor for product and engineering teams, as well as doing code and system design audits. And in fact, the research that I'm presenting today was originally identified during one of these internal audits. So the goal today is to describe these classes of attacks on SSO and SAML and how an attacker could exploit them. So at first I'll discuss SAML at a high level, so we're all on the same page for the mechanisms that enable these vulnerabilities. And then from there I'll dig more into the nuance of exploitation as well as mitigation. So with that being said, let's first get started with SAML and SSO. There's quite a bit I could cover here, but I'll cover enough ground just so these vulnerabilities seem relatively intuitive. So single sign-on is really just describing a user experience where you authenticate to one service in order to access multiple services. So in an ideal SSO world, users would benefit from this UX as they would only need to remember one really good password in order to access many services. In a generalized SSO setup, there are like three main characters. The first is the identity provider, which is often abbreviated IDP. The IDP is who you authenticate to in order to get access to these multiple services. So for example, your organization's user directory. The second character is the user agent, which is just a fancy term for a process acting on a user's behalf. And for this talk, it will always just be a web browser. And then finally, we have a service provider, which is often abbreviated SP. And the SP is the service the user wants to access. So this could be a payroll web application or some sort of chat application. So one fairly common SSO flow starts with authentication to the IDP. The IDP then generates and signs a message intended for the SP and passes that to the browser. The browser takes this message and directs it towards the SP, and the SP parses that message out, validates it, and determines how to authenticate the user, if at all. So what's notable about this particular workflow is that the browser process is under user control, and these messages are ultimately passed through it, so a service provider must be able to authenticate the contents of the message when it receives it. This is part of the problem that SAML and some of the related standards are attempting to solve. So SAML is the security assertion markup language, and it's a common standard used for SSO. There are multiple other standards that could be used for an SSO setup, like OpenID Connect, for example. But from my experience, SAML is more prevalent in an organizational context, whereas you may see things like OpenID Connect or similar ad hoc protocols in a more consumer-facing context. And really, and what SAML is defining is considering that your IDP and your SP may be built by completely different people or systems, it's a common language that's used to share data across these disparate systems. So SAML also defines how other standards interact with it, such as those that provide things like message authenticity. So I think everyone would probably hate me if I put like a real SAML document up here. So this is a very simplified example. SAML documents are just XML. XML can get like relatively nasty, so this has a lot of the cruft removed. I would, however, like to highlight a few key elements that are often used during SAML-based SSO because they are relevant to this talk. The first are the subject and the name ID elements. So the subject element is just conveying information about the authenticating user. The name ID is one part of the subject element and defined as a string value that uniquely identifies a user. This could be really any identifier, but like more commonly you'll see things like email addresses or usernames. SPs very often end up using this name ID in order to identify what user they want to authenticate when they receive a SAML message. So the next interesting set of elements are the attribute statements and attributes. So an attribute statement is just a set of attributes, and attributes are just general properties of the user that the identity provider may want to convey to a service provider. So for example, an identity provider may use a username for a name ID, but also wants to inform a service provider of the user's email for like notification purposes. So you could also, say, use the attributes section to convey, as I've done in this slide, access control roles, like this person is an administrator. And finally, we need a signature to prove that this information wasn't changed by a malicious user. And this is where the signature element and the XML digital signature standard comes into play. So SAML uses the XML digital signature standard, often said XML DSIG, to sign documents and prevent tampering by potentially malicious user agents. So what the simple signature element in the slide is conveying is that these signatures are included within the SAML messages passed within, between these systems. So at first glance, this may seem like somewhat of a chicken and egg problem. How do you sign a document that includes its own signature? But this is part of what XML DSIG and the standard is specifying. So for the most part, XML DSIG is irrelevant for this presentation, but there's one step of creating XML digital signatures that enable these authentication bypasses that I alluded to, so we'll dig into it a bit more. And this step is XML canonicalization. So as you may know, digital signatures become invalid if even one single bit changes in the signed text. Because signed XML documents could pass through multiple services and experience possibly inconsequential changes, XML documents are not signed as is. XML documents are instead signed in their canonical format. So canonicalization, which is abbreviated C14N, is a standard series of transformations that are applied to documents before signature operations. So this prevents minor differences in signed documents from causing signatures to become invalid. The key point here is so long as the documents have the same logical meaning, they should have the same signature. So a demonstration of C14N can be seen in these XML documents that I've included in the slide. So the first two are quite similar, aside from their attribute ordering being reversed. These two documents have the same canonical form because they have the same logical meaning and would therefore have the same XML signature. The last two documents are also quite signature, actually quite similar, except for the comment included in the last document. So the last two documents could have the same canonical form, but it depends on the canonicalization algorithm. Which the fact that there are multiple C14N algorithms is probably not surprising because it is XML and XML is complicated. But however, for this talk, there's only one distinction that's worth noting across these algorithms. And it's that some C14 algorithms remove comments prior to signature operations. So that is, XML comments like the ones that I included in the previous slide do not actually affect the signature. There are algorithms that do include comments as part of the canonical document, but from my research, I think those C14 algorithms are actually far less frequently used. And I believe that's probably due to this quote, which suggests that C14N including comments is merely a recommended part of the standard, whereas C14N without comments is a required part of the standard. So given this complexity of SAML and the supporting specifications like XML C14N and the XML digital signature standard, if I was a developer wanting to implement a SAML service provider, I'm very unlikely to just start from scratch. And this is where SAML libraries come in. So SAML APIs are often abstracting away all the nasty details to make developer UX a bit more straightforward. So considering SAML is also just a language to convey data, it's still up to the SP implementer to decide on what needs to be done with that data. So we can see in this code snippet here using the Python SAML API how you could probably build a very simple SAML SP. So this code snippet here is just taking something like an HTTP request object, processing it and transforming it into a SAML document object. This SAML object is then processed and checked for signature validity. And assuming there were no errors during processing, we can extract the data relevant for our use case. So in this case, we just need to extract the name ID element from the SAML XML, which is the username that we want to use to authenticate our user. So a subtle point here is that these libraries do not often use the canonical XML document for this post-processing step that's SP specific. This means that the document used for signature verification may be slightly different than the document that's used for this post-processing step. So considering SAML library authors or SP developers may need some way to extract the relevant XML data during the authentication process, it may help to get a sense on how this is accomplished underneath the hood of these SAML APIs. And this is where lower level XML APIs come in. So this code snippet is an example of what extracting a name ID may look like at the XML API level using the popular Python LXML library. So first we need to convert some string representing XML into an XML object. And then we can call a method like the .text method on that element to extract the inner text of it. The output of this code is simply the name ID value, Kelby Ludwig. I think most in here would probably guess that. So one of the key findings from my research, however, is how these APIs change when comments are included into these inner text values. So given that a comment has been inserted into the inner text of this name ID, what would the output of this code be? One might expect it to not change at all. However, the insertion of this comment would actually truncate the extracted inner text. So you may ask, why did that value get truncated? It of course depends on the implementation, but a probable answer is that XML documents may be internally represented in the library as trees by the underlying XML library. So in my first text extraction example, the document used could be seen as a tree with one root with one child node containing the full inner text. However, the second document may have 3 child nodes, so a text node containing the first part of the text, a comment node, and then a node with the rest of the text. So viewed in this manner, it may be a bit more clear what false assumption was made, and it's that a root node may have multiple text nodes as children that represents one string. So if it's assumed there's only one child containing all the relevant text, a partial text extraction may occur. Although I hadn't personally seen an example of this when I was doing my research, I've since seen some systems that actually accidentally only extract strings from like the last text node instead of just extracting the first. So that means there's a possible few variations of this type of failure, but for now we'll just assume that a comment is truncating everything after the comment. So is LXML broken? It's kind of hard to say. So other libraries do what LXML does in their methods for extracting inner text, but take, for example, Ruby's REXML. They'll also truncate text after everything after the comment, but REXML documents this behavior, so it could just be viewed as correct. But another perspective on correctness may be whether a language ecosystem is consistent. Other Python libraries like Python's XML tree has a .text method exactly like LXML does, but that one actually ignores the comment and returns the full inner text. So at best you could probably argue that this behavior is technically correct, but technical correctness may not be intuitive, and unintuitiveness may be hurtful. So some libraries, like for example Python's minidom, doesn't even provide a method for extracting inner text. Users of this library just have an XML tree API, and so they would be responsible for using an XML tree API to extract inner text and are likely to also introduce a similar issue. So at this point we know just enough about SAML to actually construct one of the vulnerability classes that I identified. So to recap what we know, first SAML documents are passed through an untrustworthy browser to convey authentication information within XML. These documents are then signed to prevent tampering, but XML canonicalization algorithms often don't factor in comments into signature validity. And on top of that, the APIs provided to SAML implementers may truncate text when a comment is added to inner text. So our attack is simply taking a section of XML that looks like this and inserting a comment into the appropriate location. And so the result is that when this is processed by a vulnerable SAML SP, the comment would not invalidate the signature, but would still cause the subject's user identifier to become truncated. So in this example, authenticating as the user admin@victim.com.evil.com would allow an attacker to truncate the name ID to a completely different user like admin@victim.com. So in other words, the comment is acting very similarly to null byte attacks. So it gives me the capability to truncate my own credential in order to become other users. So as I mentioned before, I first identified this vulnerability during an internal audit of a potential dependency. So once we identified this first instance of a single vulnerability, doing a root cause analysis suggested that this issue could be much more widespread. In fact, when doing my initial proof of concept, ended up making this same mistake as LXML and ad hoc recreating the issue myself. So testing that other people could have also made this mistake, testing that hypothesis actually turned out to be fairly efficient. With the help of a couple of other Duo researchers, we hunted down open source SAML implementations to try to identify similar behavior. So our main strategy for doing this was weaponizing existing unit tests. So what I mean by that is many open source SAML libraries often included a set of unit tests where at least one test involved extracting a name ID from a signed SAML element. To identify if a library was vulnerable, we nearly needed to take that test in that format, add a comment somewhere, and ensure the name ID was extracted properly. So this allowed us to very quickly identify multiple open source projects that were affected by this vulnerability. The initial research identified 4 open source projects that were affected: Python SAML, Ruby SAML, SAML2.js, and OmniAuth SAML. The last project, interestingly, was actually built using Ruby SAML, so the presence of the vuln ended up propagating through into a different project. Throughout our disclosure process, there had been additional projects that have self-reported being vulnerable, such as OpenSAML C++. And really, like, the interesting aspect of this particular outcome is that these are known vulnerable SAML libraries. So this means that the scope is much larger than just these 5 projects, because service providers or products reliant on vulnerable versions of these libraries are often affected. So additionally, this doesn't account for any one-off SAML implementations that may have ad hoc recreated the vulnerability themselves. And this is a subset of products that I'm aware of that were affected by this comment truncation vulnerability. This includes products such as Shibboleth SP, GitLab, a few Symantec products, and the product I alluded to earlier that we did the review of, the Duo Network Gateway. So a good chunk of these products had SAML implementations based on libraries that I previously mentioned. And for what it's worth, most of these products are on-premise. So there could be SaaS products that were affected, and some have self-reported being affected, but not everyone always publishes release notes when their SaaS service has some backend vulnerability patch, so those cases are a bit more harder to track. And finally, this is the timeline of our findings and research. As I mentioned before, I identified the first issue during an internal audit last December. 3 days after that, while simultaneously sorting out what a good patch would look like for the seemingly new vulnerability, we identified 3 other vendors that were also affected. And since we were dealing with multiple affected vendors, we opted to work with CertCC to coordinate disclosure across these vendors, as well as other common SAML IDPs and SPs. And coordinated public disclosure was done around 2 months after the initial contact to CertCC, which was about a month earlier than the initial suggested deadline. So switching gears a bit, let's take some time to look at how this vulnerability could be exploited. So given that we know that we can find vulnerable SAML service providers that allow us to truncate signed data, how could this be leveraged by an attacker? Does exploitation just require sheer luck to get an identifier that is truncates to some other target? And the answer to that is actually kind of complicated, because both SPs and IDPs are really configurable. So there's like lots of wiggle room for configuring things in such a way where risk is negatively or positively impacted. So let's first take a look at some ways that a service provider may be affected, as well as walk through an example of an exploit of a vulnerable service provider. So to be clear, the threat model of this attack first requires authenticated access to an identity provider. So initial access may be achieved through some form of account takeover like phishing, or could just be carried out by an employee looking to access a coworker's data. This initial foothold, when combined with the comment truncation vulnerability, can be used to pivot to different user accounts. So at first glance, this may be impractical, since we may be reliant on truncating the data for our foothold account, which may not necessarily lead to anything interesting. But this is where these SP-specific features or minor implementation details that vary across SPs may make things easier for attackers. So the first aspect of SPs that could lead to more interesting exploits is how SAML is sometimes used to convey authorization information. So recall that the SAML attribute statement is just some set of properties relevant to the authenticating subject. So a SAML document may use these attribute statements to inform the SPs of the user's role, like I mentioned earlier. So this adds another possible avenue for impactful value truncation. So if the attacker doesn't necessarily have an interesting user identifier to truncate, they may be able to truncate group names into something impactful. And this generally applies to any other XML element that is conveying authentication or authorization information. So in this SAML example, a user may have, say, a lesser privilege administration role, like one that is scoped to HR administration. However, if this was truncated to something like administrators, the service provider may be enabling a privilege escalation vulnerability through this particular comment truncation technique. So another SP-specific detail is how name IDs are handled and processed. So the only requirement for user identifiers conveyed via name ID is that it uniquely identifies a specific user. Identifiers could be anything from user-selected usernames to completely random identifiers. Using random identifiers is probably unlikely to be truncatable to anything interesting, but maybe things like incremental numeric identifiers could be exploitable, as numbers like 104 could be truncated to become 1. Other identifiers such as email addresses and usernames are more dependent on how accounts are registered. And since account registration is often more of a function of the identity provider, I'll discuss that a bit more when we get to the IDP exploitability part of that talk. So an interesting case study for exploitation is actually GitLab, the open source code management service. It's notable because prior to 10.7.0, GitLab was vulnerable to the comment truncation vulnerability in their SAML service provider, as they used one of the vulnerable dependencies that I mentioned early on. GitLab SAML SP implementation also highlights some of the unique processing that is done during a service provider authentication that makes it also an interesting case study. So first, to get an understanding of their architecture for identity, first GitLab maintains separate tables for their username and these external identities. An example of the latter, these external identities, would be a SAML name ID. So once the SAML document is processed, GitLab would attempt to map that external identifier to a GitLab user. If the name ID was already mapped to a user, the user is then authenticated. If the name ID isn't mapped to a user, GitLab may just create an entirely new user with whatever privileges the administrator had configured for default access. So to exploit GitLab using the comment truncation vulnerability, the attacker needs to truncate their name ID in order to match an external identifier that maps to our target user. So to walk through what this would look like, suppose that we're targeting a GitLab user with the username victim. This is not the actual username that we'd be targeting for this exploit, because their external identity, which is shown in the bottom right photo here, might be something like SAML victim. And so this is the one that we're looking to target for this truncation bug. So this is a snippet of what the target user SAML assertion would actually look like. So this is a completely normal, unmodified, benign SAML assertion. Basically, the name ID has the external identifier that we're looking for, which is SAML victim. And it's also noteworthy to see that the user's email is provided through the attribute statement element. So that part doesn't necessarily affect our ability to exploit the system. It's really just used so GitLab can keep user profile information synchronized between the identity provider and the service provider. So assuming we can access an account on the identity provider with name ID SAML victim 123, an attacker can truncate their own SAML document to collide with the target user's external identifier using the payload seen here. An interesting side effect of successful exploitation is that the victim's profile information may be updated based on attributes in the attacker's SAML document. So for example, here in the bottom picture, the attacker's account email address replaced the victim's original email address during authentication. This is not necessarily indicative of an increase or decrease in exploitability, but it's another indication that these SAML service providers often implement some amount of custom logic after SAML documents are verified. So before I get into how IDPs affect exploitability, I'd like to cover some of the remediation of the comment truncation vulnerability. So both the identification and remediation process of a vulnerable service provider depends a bit on your relationship with the service provider. So if you say manage or administrator service providers, your two best options are probably asking service providers if they're vulnerable or just spinning up a browser proxy and testing things yourself. If you're someone in an organization that has written a SAML service provider, I'd probably recommend to follow the weaponized unit test strategy to identify if your library or implementation is vulnerable. This does, of course, assume that someone wrote tests, which may be an absurd assumption, but you never know. So there are also other mitigation strategies as well, such as rejecting SAML documents that are non-canonical when they are received, or rejecting SAML documents that contain comments, which is probably fairly unlikely in most normal circumstances. But the efficacy and practicality of both of those solutions does depend on your context. Okay, so up until this point, I've pretty much heavily focused on exploiting the service provider, but the service provider is really only one part of the SSO system. So even though service providers are ultimately making this comment truncation mistake, in my opinion, most of the risk increasing features actually come from the identity provider. So what features or configurations of an IDP would influence exploitability? The first feature that one might possibly think could reduce exploitability is something like two-factor authentication. However, whether 2FA actually completely eliminates this vulnerability depends on what systems are enforcing 2FA. So if the IDP is responsible for enforcing 2FA, that may not provide additional protection from this vulnerability. Our threat model is based on a user with an authenticated session. The attacker already has authenticated access to the IDP. So while 2FA may increase the cost required for an attacker to get their initial foothold in the case of like an ATO, this doesn't really help for the threat model of malicious insiders who have the capability to provide their own second factor of authentication in order to access their own IDP. And since SAML document tampering takes place after IDP authentication is complete, identity provider enforced 2FA doesn't necessarily limit the risk of exploitation. If the SP enforces 2FA or the SP enforces 2FA in addition to the IDP, exploitation opportunities are a bit more limited. And this is because the SP would likely be extracting the user's identity from the SAML document in order to look up the user's 2FA information. And in this case, the comment truncation exploit would cause the SP to look up the victim user's 2FA information, which means the attacker would then be presented with the victim user's 2FA prompt and would have to then bypass that in order to gain access as well. So in this case, it's still a first factor authentication bypass, but there's still that second factor of authentication. Another variable that can greatly influence impact, as I mentioned previously, is how IDP users are registered. So self-registration is a pretty standard practice for consumer services, but from my experience, as I mentioned earlier, SAML-based authentication for consumer services is probably a bit less common. Organizations that are more likely to use something like SAML may manually provision all their employees. However, some identity providers do offer self-registration options, which may be used to, for example, reduce IT burden. So an attacker who takes advantage of self-service user registration for an IDP would likely increase the impact of this vulnerability, as the attacker can provision accounts for themselves. And so this gives them the opportunity to influence their SSO identifier. And if I'm able to just choose my username for the IDP that gets used in the SAML assertion, I can just pick one that matches my target user with some like junk at the end, and so I can truncate it as I need. So another potentially risky IDP feature is account lifecycle functionality, such as user profiles. So if an IDP also functions as an employee directory, employees may be also able to do self-service profile management, such as updating their first name or updating their phone number. In other words, if an identity provider allows a user to edit the data that they then use later for SSO identity, they may have some influence over how they're identified. And to describe this particular scenario, I'll use the term mutable identity to describe user profiles that exhibit this particular behavior. In fact, I think mutable identities are an interesting enough concept that it's worth digging into more, as it can kind of be its own vulnerability class. So mutable identities are interesting because users are able to influence their SSO identity. They also greatly impact or affect the impact of the comment truncation vulnerability. So just like user registration may allow an attacker to choose their own identity, mutable identities allow an attacker to update their identity in order to be conveniently truncatable. So to get a better sense of this comment or this concept, we can see an example of mutable identity in LastPass Enterprise's SSO feature. So similar to other identity providers, LastPass has an enterprise feature that gives you this like launcher view for all the service providers that a user has access to. So if an administrator had configured a user's email identifier as the SAML name ID for one of these services, the name ID would update after the user updates their account email. So this allows the attacker to update their SSO name ID to any email address they can prove ownership for. So in normal circumstances, this actually wouldn't be an issue because an attacker wouldn't likely to be able to prove ownership of a victim's email address. However, when combined with the comment truncation vulnerability, it becomes trivial to use mutable identity to target any user. So this is what an example exploit steps would look like in order to combine the comment truncation vulnerability with mutable identities. So in this case, I'm acting as myself, an employee within Duo looking to target our CTO, Jono. So I first need to find a SP vulnerable to the comment truncation vulnerability that uses email addresses for identity. So this can be detected just by authenticating to services that I have access to and inserting comments into SAML assertions and observing responses from SPs. So like things like error responses or maybe default user access is a good indication that a service is vulnerable. So once a vulnerable SP is found, I can update my LastPass account email under a domain I own. So for example, pretending I own attacker.com, I could use the email address jono@duo.com.attacker.com. Since I own attacker.com, this is an email I can prove ownership of by following through LastPass's confirmation email. And so once this email address is confirmed, my LastPass profile is updated, as is my name ID used for LastPass SSO. And then I can re-authenticate to the vulnerable SP, insert a comment for my domain, attacker.com, and authenticate as my target user. So I've actually recorded a demo of this exploit workflow using LastPass Enterprise SSO and a demo SAML service provider that is vulnerable to the comment truncation vulnerability. So this first video demonstrates LastPass's SSO workflow, as well as the demo vulnerable service provider who just logs who I've authenticated as. So you'll see I'll start the attack with a, let's see if I can get this, with my standard organizational email like my name @duo.com, which you can see there. And then once I authenticate through LastPass SSO, my LastPass name ID is just shown in the service provider's UI. So completely normal SSO workflow. This video demonstrates how LastPass email update functionality is mutable by end users within a LastPass enterprise organization. So here I'm updating my email address from one in my organization, so my name @duo.com, to target the email address of Duo CTO under a domain I own, which is jono@duo.com.kel.bz, which I don't actually own attacker.com, as cool as that would be. I can confirm this email since I do own this domain. And then finally, after proving email ownership of that domain, which I did out of band, my LastPass account email has been updated. So this video demonstrates my ability to authenticate as a different user in my organization using the comment truncation vulnerability. So you'll note at one point in this video, I enable a browser extension, which is this little blue circle in the top right corner. And that's really just a browser proxy that's inserting comments into the appropriate location automatically as SAML messages are passed through my browser. So here I first killed my previous SP session because I had already authenticated. And so after doing a re-authentication, you can see that my email address has been updated to the one that I just proved ownership of. And then after killing my session and enabling my browser proxy, I can re-authenticate, which inserts the comment in the appropriate location in this new email address and allows me to target jono@duo.com. So just as I demonstrated, mutable identity is a great pairing with a service provider that's vulnerable to the comment truncation bug. But in some cases, mutable identity could just be a vulnerability on its own. What if I could just edit my identity to become someone else? If my IDP was configured in this way, an attacker may not even need a comment truncation vulnerability. They may just be able to indirectly choose their name ID. And so during my research, I actually found a fairly straightforward path to this behavior in Okta. So for context, Okta is an identity service that provides users with an SSO experience similar to what I described with LastPass. The path towards choose your own identity for users just required the usage of 3 features. The first feature was that Okta allows a service provider to use a programmable identity. So instead of configuring each user's identity on a case-by-case basis, you could use their expression language to provision identities under a common format. So if your organization uses a standard username format like first name dot last name, this makes provisioning accounts much easier. Okta also gives users editable account information once they're authenticated to their IDP. Some of this account information was by default writable by a user at the time of this research. So for example, a user could update values such as their first name, their last name, or email, and ultimately Okta would end up using these editable values for previously mentioned programmable identity. So at first glance, this seems like it's a fairly straightforward path because a user could update their profile information, which then gets used to an SSO gets used as their SAML name ID. So for example, if I use my first name and last name for identity in an SSO context, I could just change my first name and last name using the account update profile functionality. But there was actually one more trick to making this work. It wasn't that straightforward. Okta didn't actually provision these programmable identities on a per authentication basis. So if you were previously provisioned an account and you updated your profile, your identity wouldn't change on that next authentication like you've experienced with LastPass. However, there was a third feature that made this vulnerability possible, which was a self-service application portal for users. And what this feature would allow is directory administrators could allow their users to opt into or opt out of applications that they have access to. So this could, for example, be used to clean up a user's UI if they have access to multiple applications but only end up using a few. This feature was not enabled by default at the time of the research, but if this was enabled and used with programmable identities, a user could use it to deprovision their application and then reprovision themselves from an application, which would cause their identity to be, or account to be reprovisioned, and they would have complete control over their SAML name ID used in an SSO. So identifying or exploiting this issue would have gone through these high-level steps. So you just update your profile information and deprovision yourself from a target service provider. And after reprovisioning and using the self-service application management portal, you could re-authenticate and inspect the SAML document that was issued. If it had not changed, you could try again with another application. If your identity had changed, you could use the same set of steps to target any user that you want. It does depend a bit on how these usernames were programmed, but in some cases, you may not even need a comment truncation vulnerability at all. So if you were a user of Okta's dynamic expressions and or user expressions and you wanted to remediate this, you could do so by either avoiding programmable identities or just avoiding them with writable user attributes. Okta's remediation plan for this issue, when I first reported it, was to mark some of these profile attributes that I mentioned earlier as read-only by default for new organizations. At the time, there were no stated plans to change existing organizations, but prior to this presentation, Okta did state that they worked with customers to disable mutable user attributes in existing orgs, but I don't have timelines or context on the scope of that. So if you use these features, it probably wouldn't hurt to spot check your configuration. And it's worth noting that in general, it's still possible to configure an application in this way. But the changes that Okta made for new organizations made this footgun a lot easier to avoid or a lot more difficult to stumble across by accident. So to wrap things up, so I hope this talk demonstrates that even old and frequently used systems may have some interesting vulnerability classes lying dormant underneath piles of complexity. And I'd also like to emphasize that we could only look at so many systems, and I hope this talk inspires a few folks to go out and look at their own SSO setup and see what they can find. And then finally, I'd like to give a shout out to CertCC and Duo for supporting this research and the coordinated disclosure, as well as big thanks to any vendors who provided patchers to their users. And with that, thank you all as well for coming.